Hi everybody, here we are again in the barn. Well, today we're going to do a quick little electrochemistry lab for you, and I'm going to make some batteries. I mentioned in one of the other videos that in the past we've made batteries with beakers of solutions and salt bridges, but today what we're going to do, this is one of those Mr. Wizard days, we're going to use small strips of filter paper. And I'm going to put a little puddle of copper plus 2 ions and then a little piece of copper metal in it. I'm going to put a little puddle of zinc plus 2 ions on this end of the piece of paper and put a little piece of zinc metal in it. And then, like I mentioned before, for a salt bridge, I've got a bottle of potassium nitrate back here. I'm going to swab a little wet spot between the two spots of copper plus 2 and zinc plus 2 to act as a salt bridge. And then, in the past, what we've done is use the computer as a fancy voltmeter and just put the electrodes from the computer on the battery and see what kind of voltages we get out of them. Well, I decided not to use the computer. We're going to use an old-fashioned voltmeter. All right, well, let me set up a couple of these. And actually, I think what we need to do is let's go to the blackboard first, and I'll explain a little bit about these first 3 batteries that we're going to make. And then we'll come back here and make them and read their voltages. Okay, well, as I just mentioned, we're going to use filter papers to make our batteries, and it uses only a few drops of solutions, and the battery runs plenty long enough for us to measure a nice voltage out of them. And today what we're going to do is use lead as the electrode on all 4 of these initial batteries that I'm going to make. And the reason is we're going to measure the reduction potential then of 4 other metals, actually 3 other metals, versus lead. Now that means we're choosing lead then to be sea level. All these voltages will be measured above and below the ability of lead to be reduced. Okay, now the first one, and again, like I said with the filter papers, we're just going to put a few drops of lead nitrate at the end of, at each end of the 4 batteries. And it's 0.1 molar lead plus 2. On the other end of the batteries, we're going to put copper, zinc, lead, and iron. And under each piece of metal, put a little 0.1 molar puddle of its ion. So that, again, there's an equilibrium possibility there. In each case, then, I'll swab a little bit of potassium nitrate, just a wet spot, between the 2 puddles to serve as our salt bridge. Now, there's one battery here that I'm not going to do. I originally wrote it in the lab, and I had a lead-lead battery with molarities of lead the same on both ends of the battery. Well, clearly this is not going to give any flow of current, and sure enough, we always got 0 voltage. So in our demonstration, I think I'm going to eliminate that one, and we can just pretty much say that it has 0 volts. All right, so on your report sheet, when we get to that part, we'll put in 0 volts for this. Okay, so when we measure the reduction potential of copper then against lead, I think you're going to see that copper likes to be reduced more so than lead. So we're going to get a positive voltage. We're going to use the black lead on my voltmeter here because that'll make the lead the ground. And we'll be measuring the potential for reduction at the other end of the battery. Well, this one comes out a positive voltage on the order of around, I was thinking it was around positive 400 to 500 millivolts, 0.4 volts to 0.5 volts. And the zinc, on the other hand, actually likes to be oxidized, so it's not gonna go positive. The battery's gonna run in reverse, and we'll get a negative voltage here. Usually, again, around negative 400 to 500 millivolts. I'm sorry, I'm talking in millivolts. But again, you'll see that this gives us a nice significant negative voltage. Now, again, we're not going to do the lead-lead battery. We'll just tell it it's 0.00 volts. And iron, the iron little pieces that I've got, I got them from the welding department, and some of them were a little rusty, some not so. And so it depends on how rusted it is as to what voltage you get out of this battery. It turns out iron plus 2 and iron plus 3 have reduction potentials pretty close to that of lead plus 2. So it usually hovers pretty close to 0 volts. Well, I shouldn't say that. Maybe 40 millivolts either side of 0. There's a big window depending on how rusty that piece of iron is that I choose out of the pile to make the battery with. But again, we're just looking to show you that sure enough, it's an easy task here to make a little battery, measure their voltages. Now, once we've done the first 3, they're going to ask you the question, well, what would happen if we made a copper zinc battery? We know that the copper reduces more so than the lead, and the zinc would rather oxidize. What if we pitted these two against each other? Well, we've made our own little electrochemical series here, like our own table 20.1. Only we chose lead to be sea level, not hydrogen. And so you can understand then what they're getting at. If this one was 4 to 500 above sea level and this was 4 to 500 below, it's kind of arbitrary what we chose to be our reference point. As long as they're both measured to the same reference, then I could say, well, the relative difference here should be the voltage of a copper zinc battery. All right, well, I think we should make one of those. Let's do these first three first, and then we'll come back to that question. Okay, well, I've prepared our three batteries here. I've got 3 strips of filter paper. I've got 3 pieces of lead that I'm going to use for the reduction side of my battery. I'm going to put the black lead, the ground lead, on the leads because I want to measure the reduction potential of copper and zinc and iron in comparison to the lead. Now I'm going to do these batteries one at a time because sometimes they'll dry out by the time I get to the end. So let me go ahead and put the solutions on this one first, and we'll come back and measure the voltage. Now you'll notice my voltmeter is reading a few millivolts. If we just short it out and zero it, it should go down to maybe a millivolt or two. It's running down there around 8 or 9 millivolts. Let me see if I can short it all the way down. Oh yeah, now it's down to 0. Okay, so we've calibrated. Let me go ahead and fade out here, and I'll come back and measure the voltage. Okay, well, for our first battery here in front with the copper and the lead, I've got a solution. I thought I did. I've got a solution of 0.1 molar copper nitrate. I'm just going to put maybe a dime-sized spot of liquid here. And on the other end, I'll put about a dime-sized spot of lead plus 2 ions. This was lead plus 2 nitrate. Now I'm going to swab in between the two just a wet spot of potassium nitrate to act as our salt bridge. Now I always like to press the copper down into the ions a little bit just to make sure that there's good contact there, and the lead likewise push it down into the solution real well. Now we're going to put the black lead on the lead. We're going to put the red one on the copper. Let's see what kind of voltage we get here. Oh, we're up in the 0.419422. Yeah, this is 400 millivolts, 420 millivolts. It's kind of jumping around there. We'll just pick a number here. Oh, it's up to 434. I think our salt bridge is kind of catching up with us here. Seems to be leveling off at about 437, 438. Let's call it 438 millivolts. All right, well, let me set up the next one. Okay, this time I'm going to use a little 0.1 molar zinc on this side with a piece of zinc metal. And again, not a very big spot, maybe a dime-sized spot. I put a little piece of cardboard here because I needed something a little stiffer to press down against. And a little bit of the lead on the other end of our battery. And again, a little wet spot of potassium nitrate to act as a salt bridge. Just swab a streak in between. I'm going to put the piece of zinc into our zinc solution, zinc into our battery, and the lead. Now, I should point out that the voltage on our last battery was positive, given that the copper likes to be reduced more so than the lead. Now, in this case, again, I'm going to put the black lead on the lead side and the red on the zinc, and let's see what kind of voltage we get here. Now this time, I don't know if you can see this, there's a negative sign in front of our voltage. And it looks as if it's going, negative 393.8. Well, we're at minus 394 millivolts. And it seems to be holding pretty steady there, minus 394. Oh, there's 393. Let's call it minus 394 millivolts. And I'm going to kind of recalibrate here. Everything looks pretty good. Okay, so we had definitely a greater chance for, or greater potential for reduction from the copper, more so than the lead, to the tune of several hundred millivolts. And here we're seeing that the zinc would prefer to be oxidized, again to the tune of several hundred millivolts. All right, well, let's do the iron, and then we'll go back to the report sheet and fill in some of the numbers. Okay, well, this time I'm going to use a little bit of iron nitrate, 0.1 molar down on this end of the battery. And we find that iron has a reduction potential very close to lead. And so this usually hovers right near 0 volts, sometimes, plus or minus 20 or 30 millivolts. And again, let me put the salt bridge. I put a splash of lead and I put a splash of iron, and now a splash of salt bridge in between. And depending on how rusty the piece of iron is, whether it's in its iron plus 2 or iron plus 3 state, like I said, we get voltages that are usually plus or minus 30 or 40 millivolts. Oh, I'm sorry, I timed out here on my voltage. So let me get my voltage set back up. Let me re-zero. All right, here we go on the iron. Well, we're getting a little bit more. I said plus or minus 30 or 40 millivolts. It looks like, it's heading towards 0. It's going on the negative side now. Like I said, it hovers pretty close to the bottom. And it looks like now we're at minus 16, 17 millivolts, 18. Let me let it settle in here for just a second. You can see that these batteries are much easier to make, much less solution to use. Consequently, we can, if it doesn't work out, we can always make another battery very quickly. Well, it seems to be settling in at around minus 25, let's say 26 millivolts. We'll just leave it right there. Okay, well, let's go put these on the report sheet, and then we need to come back and make one more battery here before we move on to our Nernst equation part of the experiment. Well, let's put some of these numbers into our report sheet then. Let's see, the copper was 0.438 volts, 438 millivolts, so let's put in 0.438. That was positive. Let's see, the zinc was a negative 394 millivolts, or 0.394 volts. Again, we didn't do the lead. We assumed it would be 0. And the iron came in at a whopping minus 26 millivolts, or 0.026 volts, negative. Now, the very next questions, let me scooch this up a little bit, ask you, well, according to your table, which half cell reaction has the greatest tendency toward reduction? Well, again, we're measuring these all as reduction, so the one with the greatest potential then would be the one with the greatest tendency toward that, and the one with the least voltage would be the one that had the greatest tendency toward oxidation. So I'll leave that up to you. It's pretty obvious. Now, number 2, this is based on your electrochemical series. What would you predict the voltage of the copper zinc cell? And show your calculation. Well, the copper was at 0.438 volts. But the zinc was clear down at minus 0.394 volts. We need to take the difference between this very positive one and this very negative one. So let's subtract them. This ends up being 0.832 volts. So we would predict, let me slide this down again, based on our electrochemical series, that the relative difference here between these two would be 0.832 volts. Okay, well, we made the 3 batteries, and we pitted iron and copper and zinc against the lead plus 2. And again, we chose lead plus 2 to be our C level today. it was our zero voltage. And so we're measuring reduction potentials compared to lead. This again was just to illustrate the fact that it's arbitrary where we choose the reference point to be. For instance, the book and everybody else chooses hydrogen as the reference point for all reduction potentials. And so again, as long as we all agree that that's the reference point, what we're interested in is the difference between reduction potentials. And it doesn't matter what those were measured against, as long as we all agree that we measured them against the same thing. Well, today we're doing this against lead, and we saw that copper likes to be reduced more so than the lead, and the zinc likes to be oxidized, given its negative reduction voltage. So now they go on to ask you, well, now that we see that the copper was several hundred millivolts above the lead and the zinc was several hundred millivolts below, what do you predict the voltage would be between copper and zinc? Well, it'd be the relative difference. All right, well, with that in mind, let's go ahead and make one and see if we came out pretty close. Okay, I got something here a little stiffer that won't conduct electricity that I can wash off a little bit. Now this one is a copper zinc battery. We just wanted to predict based on those voltages we just saw, well, what kind of voltage would we get then if the copper was several hundred millivolts above, like 450 or so, and the zinc was below? Well, again, we should probably see a potential of 800 or 900 millivolts between these two. So let me put a little splash of copper on one end, a little splash of zinc on the other. And again, for our salt bridge, just a little swab of potassium nitrate between the two. Set our copper piece in, set our zinc piece in. I'm going to zero our voltmeter. Okay, and now black one on the zinc. And sure enough, we're getting up there above 800 millivolts, positive 800 millivolts. Looks like it's settling in at 820, 826, 830. We'll give it a second, let the salt bridge catch up with us a little bit. And again, all I've done, I don't know if you can see this, all I've done is put the electrodes directly on the pieces of metal here with the copper and the zinc. And it looks like 8. Oh, it's climbing, climbing, climbing. Again, the salt bridge is kind of catching up with us. Looks like it's dropping now. It went up to 858 millivolts. Let's use that. 0.858 volts. Okay, well, once we built that copper zinc cell, looks like we came in pretty close. 0.858 volts compared to our predicted 0.832 volts. All right, so our electrochemical series that we came up with, our little table, was reasonably close. All right, well, this was kind of a get to know the batteries section of our lab. We intended this first page for you to kind of get your technique down in building the little paper strip batteries. But we've got bigger fish to fry with the Nernst equation, so let's get on to the Nernstian portion of our lab. All right, now in this next segment, we're going to do 5 batteries. I may do 3 at a time. Actually, I think we've got 6. We've got 5 standards, and we've got an unknown. You see where this is going. All right, so we've got 6 batteries to make. I usually make 3 at a time because they have a tendency to dry out by the time we get to the end, and if they dry out, they don't work very well. So in essence, I'm going to put 1 molar zinc on the end of each of the 6 batteries, and I'm going to start with 1 molar copper on the first one. So that first one would actually represent, if you stop and think about it, E0, where both of the concentrations of the zinc and the copper are 1 molar concentrations. Well, then I'm going to decrease the copper concentration down the line, and then I'm going to do an unknown. Well, you can kind of see that we could compare the voltage of the unknown to where it lies in the stack and kind of get an estimate of what its molarity was. Well, let's go to the blackboard and talk about that, and then we'll come back and actually make those 6 batteries. Okay, well, in this Nernstian section of the lab, and you understand the concept here with the Nernst equation, it shows how voltage varies when you vary the molarities of your reactants. So we're going to set up batteries and change the molarities of one of the reactants. We've got 5 copper zinc batteries. And we're going to put 1 molar zinc at the end of all 5. Actually, there's a 6th one down here with an unknown copper molarity. So we'll have zinc at the end of 6 batteries. We'll put copper at the other end of all 6. Only 1 molar zinc at one end, 1 molar zinc of copper only on this battery. So keep in mind that if it's 1 molar on each end, then this would essentially represent our real world E0, our standard voltage. So we're going to compare our real world voltages to what the Nernst equation would predict for these batteries. And when we do so, we're going to use this E0, our E0, in the Nernst equation for our comparison. And that way we're comparing apples to apples. All right, well anyway, we're going to decrease the copper molarity down the line. The next one will be 0.1 molar, next one 0.01, 0.001, 0.0001, and then an unknown copper molarity. And essentially we're just going to go down the line then, and with my voltmeter, measure the voltages of each of those. And I think you'll see that there's a steady decrease in the voltage, which would be predicted by the Nernst equation, since copper plus 2, the ion that's underneath here, underneath the pieces of metal, is one of the reactants. If we decrease the molarity of one of the reactants, likely we're going to decrease the voltage. And I think you'll see that that's exactly the case. Now, before we go too much further, before we actually go to measure the voltages, let me show you what we're going to do with them when we're done. Okay, so the Nernstian take on our copper zinc cell, and remember the Nernst equation is that the measured voltage of the cell is equal to E0, the standard voltage, minus 0.0591 over N log of Q. Now the reaction we're running today is zinc solid plus copper plus 2, kind of reversing and going to zinc plus 2 and copper solid. So the N value is not hard to figure out. I mean, if you look at this, zinc is going to zinc plus 2, copper plus 2 going to copper solid. There's an exchange of 2 electrons here. So we know that the N value here is 2. And the Q expression is pretty easy. Since solids don't appear in the equilibrium expression, it would just simply be products over reactants. The zinc molarity raised to the first power divided by the copper, likewise raised to the first power. So again, that's pretty straightforward. Now we sent you some graph paper today because we're going to measure the voltage of our 5 batteries. And you can see that the voltage changes as the value of Q changes. The zinc molarity is going to stay the same in each of our 5 standard batteries, but we're going to change the copper molarity. And so we should see a change in voltage reflected there. All right, well, let me do something with the equation. I want to take this term of the equation and I want to put it out in front, put the E0 last. So meaning that E measured would be essentially equal to minus 0.0591 over 2 log of Q plus E0. I just reversed the 2 terms. Now the reason I did that is we sent you this graph paper and I sent it to you with the axes all labeled and everything scaled so that we could plot the measured voltages of our 5 standard batteries, not the unknown, but the ones that we know. And we could plot those by putting the measured voltages on the y-axis. If we put the log of Q, and again, we know the values of Q for each of our batteries because we know the zinc molarity and the copper molarity we used. If we took the log of that number and plotted it on the x-axis, you'll notice that everything out in front of that log of Q is a constant, meaning there's a linear relationship then between the log of Q and the measured voltage of the cell. All right, well, and notice that it's going to go through a y-intercept equal to our E0. Remember, we're not going to use the book standard E0 here. We're going to use our E0, the voltage from our first battery that has 1 molar on each end. And again, that's because our voltage is going to be a little less than what the book would predict based on the fact that there's a little bit of resistance in our circuits and so consequently a little voltage drop. All right, so we're going to have you make a little graph then of E measured versus log of Q. We're going to use that plot then to look at the voltage of our unknown. And we're going to do this the old-fashioned way. As a matter of fact, let me just make a quick sketch for you. Our graph is going to have E measured on the y-axis. It's going to have the log of Q on the x-axis. Your data points should go in a straight line. with a negative slope. The slope theoretically should be equal to minus 0.0591 over 2. And you're going to find that the data points probably zigzag a little bit. I always joke that the Nernst equation is linear like a dog's hind leg is linear. It zigzags just a tad. So when you go to put your data points on here, since we don't have the luxury of the computer to do the nice linear fit for us, I'm going to ask you to do a little cheating here. I want to take a straight edge. I want to lay it on our E naught. Whatever that value is on our first battery, lay your straight edge on that point. I want you to shoot a best straight line eyeball fit of a straight line through those 5 data points that we've got. We're going to assume that our graph did go through the correct y-intercept, which would have been our E naught, but we're just going to eyeball the line. Now the reason is that we're going to use this graph then to figure out the molarity of our unknown copper. The way we're going to do it is this. We're going to take the measured voltage of our unknown. We're going to just pencil out here on the graph, and I'd like you to actually draw a little set of crosshairs like this on your graph and show me the corresponding log of Q. If we know the log of Q value, from this we can actually calculate the molarity of the copper. Now I want to do an example of that, but I'll save it for the very end. Let's go and look at our voltages, and then we'll come back. Well, in my first demonstration, these things started to dry out too fast if I set too many of them up. So I'm going to do them one at a time. Now, this first one that we need to do for the Nernst part of this experiment is to do a 1 molar zinc and a 1 molar copper. So I'm going to put a little splash of zinc down at one end. Now keep in mind, 1 molar on both ends means that this should represent really our E naught. Now remember, the book's E naught value for this battery is 1.10 volts if you went to the standard reduction potentials. But that assumes a perfect world where there's, no resistance in the circuit, so we're not likely to get exactly the 1.1, but we'll get up there close. All right, I'm going to swap my salt bridge on there. I'm going to put a piece of copper on the copper end, piece of zinc on the zinc end. Let's put our electrodes on here and see what we get. I'm going to zero this. There we go. And this should pop up there, in the 8.9 range. Yeah, we're at 0.889, 0.897. So we're getting up there pretty high. I mean, 1.1 is the standard voltage. We'll let this settle in a little bit and see where it levels out. Looks like 0.890 seems to be its favorite spot. So let's call that 0.890 volts for this very first one. And again, we're going to use this in our calculations as our E naught value. Okay, this battery, I'm going to do the 1 molar zinc again on one end. But 0.1 molar copper on this end. Salt bridge. Same piece of zinc, same piece of copper. Electrodes here. Black on the zinc, red on the copper. Oh, I'm sorry, let me zero again just to make sure. We might as well zero in between each one. There we go. All right, and so the voltage looks like it dropped a little bit. It was at 890. We're down at 0.832, 831. Dropping a tad. Looks like, well, we'll give it just a second. 826. It's fluctuating between 825, 826. Let's just call it 825. 0.825 volts for that one. All right, well, let's move on and we'll do the one with the 0.01 molar copper. All right, I got the zinc on there, the 1 molar zinc. I said 0.01 molar copper. Let me get the right bottle. So we got 0.01 molar. Sorry, I didn't get much up there. We're going to need a splash of salt bridge. Complete our battery. And now, let's put a piece of copper in, a piece of zinc on. Let's see what this voltage comes out to be. Black on the zinc, on the 0 again. Looks good. Okay, we were at 8.2 something before. It's dropped a little bit more. 0.804, 803. It's kind of sticking right there. Let's just call it 0.803. Okay, I got my 1 molar zinc on there. This time we're going to 0.001 molar copper. Getting more and more dilute each time we go down another step. Salt bridge. I'm going to set these other copper solutions out of the way. We did the 0.01, we did the 0.1, and we did the 1 molar. So we got our salt bridge on there. Here's our piece of copper. Here's our piece of zinc. Press them in there. Okay, let me get my electrodes. 0. And it looks like this voltage is coming in at about 0.78, give or take. So it dropped again. 0.777. That looks like a nice lucky number. Let's take that. 0.777. All right, a couple more to do. Okay, here we go. 1 molar zinc on one end. 0.0001 molar copper on the other. Little swab of salt bridge. More there at the end. My piece of copper metal, copper puddle, zinc in the zinc puddle. Let's zero our electrodes. And let's get a voltage. Okay, this one's coming in, well, lower. Oh, it's dancing a little bit. See if I can get it to settle down here. That looks pretty good, about 743. I think we were at 777 last time. Okay, so let's call it at 743. All right, now, one last one to do, and this will be our unknown copper solution. All right, here we go. 1 molar zinc. Unknown copper. Little splash of salt bridge. Copper in there, zinc in there. Let's zero our electrodes. Down to zip. There we go. Here's our voltage. Well, zipped in there and it just stopped right about 0.844. .838, 37. Let's just call it right there, 837, 0.837 volts. Okay, so we've got the voltage of all of our knowns, and now we have the voltage of our unknown. Okay, well, let's go to the report sheet then, now that we've collected all these numbers. and put them in and see if we can come up with a reasonable plot and the molarity of our unknown copper. Okay, well, we got a lot of numbers. Let's put them in here. Now, column 5 is where the measured voltages that we had for the different standard batteries goes. So let's go ahead and put them in. The one that was for the 1 molar, which we are going to consider our E naught, by the way. This value is 0.89 volts. When we drop the copper molarity to 0.1, this fell to 0.825 volts. 825. When we dropped the molarity to 0.01, it fell to 0.803 volts. 0.001, it was down to 0.777 volts. And the last one at 0.0001 molarity for the copper, it fell to 0.743. Now we're going to consider this our E naught, and I'm going to have you manually calculate the Nernstian voltages, the theoretical calculated voltages for these cells. But to do that, we need the value of Q, and we need the value of the log of Q. So I've conveniently made columns for you in the report sheet for that. Now notice that this, zinc plus 2 over copper plus 2, this equals Q. Well, 1 divided by 1, that's easy. The first one is 1. The second one, 1 divided by 1/10 is 10. The next one, 1 divided by 100th, oh, that's 100. Oh, this one's 1,000. And this one's 10,000. Okay, so the Q value went up considerably as we were decreasing the molarity of the copper. Now, the bigger the Q value gets, remember that means that it's products over reactants. So that means we have a lot of products down here. The voltage is going to really drop off, and it did. Now, if we took the logarithm of Q, just to make things easy here, the log of 1 is 0. The log of 10 is 1. The log of 100 is 2. 1,000 is 3. 10,000 is 4. Now, if you recall from our discussion, we are going to make a plot with the voltages on the y-axis and the log of Q on the x-axis. So I've conveniently sent you a piece of graph paper that has the axes all labeled, and they've already been ticked off to scale so that all of this will fit. All right, now I'd like you to calculate the Nernstian voltages out here. Just a reminder that the Nernst equation says that this Nernstian voltage would be E naught, which in our case is going to be 0.890, minus 0.0591 over 2, that's the n value for this equation, times the log of Q, which, by the way, we have right here in this column. So we know the log of Q for each one of these. We know that E naught is the same for every one of them. So the only thing that's going to change from box to box is the log of Q. It'll be 0 for the first one, 1 for the second one, 2, 3, and 4. So pretty easy to figure out, well, how much is going to be chipped away from the 0.890 volts. Now you're going to see that our voltages probably fell a little bit more rapidly than the Nernstian voltages, and that's because of the resistance in the circuitry in our measuring devices. As a matter of fact, they ask a question about it down here later. But first, let's put in the voltage of our unknown. We're going to need this here in a second. The voltage of our unknown was 0.837 volts. So it apparently fell kind of in this range, just above the 0.825. So I would suspect that its molarity might be somewhere in that 0.1 range, or maybe a little higher, hard to say, but somewhere in this range. All right, well, the questions, let's get to them. Question number 1 said, how do the measured and calculated values for the Nernstian voltage compare? Our actual ones and the Nernstian ones.
Well, they did differ slightly, and again, it's because of the electrical resistance in the circuitry. So basically, just address your answer to the idea that, yes, some of the voltage was consumed because of the resistance in the voltmeter and in the cables that we used and in the paper. Now, the graph. I'm going to show you mine. Oh, let me see what happened. I've got a copy of my graph here somewhere. Okay, let's see. My graph, the data kind of, like I said, came out with a negative slope. And this is the graph paper that I'm going to send you. It's got everything all ticked off for you. So I kind of sort of plotted in the data points. What I'd like you to do is take a ruler. Let me shrink this up a little bit so you can see the whole thing. What I'd like you to do is, once you've got your points plotted here on your graph, is take a ruler and try to just draw the best straight line that you can through those data points. Let's see if I can do that. So that you're kind of splitting the difference between all of them. So again, try to make the deviations about equal on both sides of the line as you draw your straight line through there. Again, a couple data points will be above, a couple will be a little bit below. Once we've established that line, then we'd like to take the voltage of our unknown, which was 0.83 something, I think, and over to the line and find the corresponding value. Oh, let me scooch down here. Find the corresponding value of Q. All right, looks like it'll be somewhere in this range. All right, so I'd like you to do the graph, draw the crosshairs on there, give me a value of Q. All right, well, let's go back to the blackboard and kind of wrap this up.
Okay, so looking at your graph, should have a negative slope. Again, if we take the voltage of your unknown and pencil in an approximation of the log of Q. I'm just saying, suppose your log of Q came out to be something like 2.1. I'll let you just round to the nearest tenth down here since we're eyeballing this on our graph. Well, that means Q, if the log of Q is 2.1, then Q would equal 10 to the 2.1. And since that, whatever that value comes out to be, is equal to the zinc molarity over our unknown copper, and we know that the zinc was 1 molar, then in essence all we have to do is take the inverse of this number, and that will tell us the molarity of the copper that was in our unknown. So again, please make sure that you show this calculation on your report sheet and indicate on your graph what you thought the log of Q was based on the voltage of our unknown. And include that graph with your report sheet when you submit everything, along with the pre-lab. Now again, question number 2, I think on the back of the report sheet has you kind of go through an analysis of how to calculate using the linear regression that the computer would have generated for us. But since we're not doing it that way, all I'd like you to do for question number 2 is go in here and just pencil in, estimate the log of Q, go through these steps, and tell me the concentration of that copper unknown.
Once you find that value of the log of Q, I'm sorry, I said Q, but I meant the log of Q, from your graph, that value is equal to the log of the zinc molarity over the copper molarity. So you're going to have to take an inverse log of that. Then the zinc molarity is 1, so it's pretty easy to figure out what the copper molarity is. This last question has to do with how did the slope of our graph come out compared to what the Nernstian slope should have been. Now, I only want you to answer 2 of these 4 questions that are embedded here. I'd like an answer to this. What should the slope of the line be equal to according to the Nernst equation? I discussed it earlier in the video. If you have to rewind it and go back there and find it, please do. And then I said, what is the significance of the y-intercept? That is, what does it represent? Again, that was covered just moments ago in the video, so you can rewind and find that. But please answer those 2 questions. Now for your report sheet, again, just make sure that you've answered all the questions here in this one. This is the critical calculation. Give me the molarity of that unknown copper solution. And again, make sure that you've calculated these Nernstian voltages. I'd like the report sheet, I'd like the pre-lab, and I would like a copy of your graph. Now, also, I'm sending out a quiz with this one. It was the one over the KSP and thermodynamics. It has a little calorimetry on it. You have a week to turn that in. I would like the lab reports in by Thursday midnight, but I'll give you till the following Wednesday to turn in the lab quiz. All right, well, let's go back to the blackboard and we'll wrap this up.
Okay, well, that pretty much wraps it up then for labs from the barn for today. Hope you enjoyed the Nernst equation and making batteries with me. Now be sure that your report sheet's completely filled out. Make sure I can see the lines and points on your graph and your pre-lab. Now I didn't go over the pre-lab, but I think if you look at the Nernst equation, it's pretty clear how that whole pre-lab piece fits together. All right, well, next week we've got, oh, and also the lab quiz. I attached it to this last email, so again, make sure that you get that submitted. Now you've got a week to work on that one, so you got a little bit of time to procrastinate. Next week we've got one last little demonstration for you, a little simulation for radiation for our last chapter. And so I promise this will be the very last submission for lab, and we'll pretty much have wrapped it up. So anyway, thanks for hanging in there for this last half of the semester. I know it's been rough on everybody, but again, you've all been real troopers. All right, well, anyway, one last lab, and I'll see you next week. Labs from the barn. So long.